Yes. You have everything you need to get all the Chapter 3 binaries.
No, for assignment. But
Oh, no. And you won't even, not even after this class. After next class, you'll have.
And it was March 3rd, 2nd, the deadline.
Yeah, it's, yeah,
So-
it's not for a while.
So it's Tuesday, 2 weeks from now.
Yeah, I'll make sure you have enough time to do it.
Yeah,
But it's just, I think you should still be doing binaries, MetaCTF binaries. I think that's probably enough. I would be surprised if people are all done with the binaries and are itching for the next assignment. But
do we have any more binaries after this?
there are some, but they're easier. Yeah, yeah. The heavy duty ones are in this
That's more
chapter.
too difficult.
And then, okay, so some people asked about extra credit after the midterm. I do have some extra credit Chapter 3 binaries. And these are harder ones, but they come with a screencast walkthrough of each one of them. So that'll be the extra credit. Yeah, they're pretty good. They're pretty good.
Are you going to release those anytime soon?
I was gonna wait towards the end, maybe the last week of class. Yeah, because they're optional. In fact, there's another person at another university who just borrowed all of the ones that I was that set to teach format string vulnerabilities. Just been borrowed, so I'm hoping it works out. But we'll see. It's the first time.
So these optional binaries are more focused toward that.
Yeah, it's a specific vulnerability of using printf without a format string, and in order to leverage that, you really need to understand the stack and pointers and these sorts of things.
So basically, it's an intro to your intro to malware.
Yeah, it's actually an intro to CS591, 491, 591. So Charles Wright teaches that one, and he does all the vulnerability things. This just happened to be a vulnerability one, but I do mostly stuff after you have compromised the machine in the malware class. So, yeah.
With the structs binary, the first one, the general methodology is figure out where this function is being pointed to in the stack, and then essentially have your pointer go up through the stack to find that spot, right?
Yep.
Okay.
And so you need to use your knowledge of how big that struct is to sort of guesstimate the number needed to hit that thing.
Well, it has to be in the same. It has to be an offset of that struct size.
Exactly. So this is where your knowledge of struct, you have to at least size it properly. I mean, you could try and brute force it, but it's painful. But you can get around the ballpark and then, tweak the number.
Well, I have the number, and I was able to brute force it by just setting the constant where it is, because I knew where it was. So I was like, hey.
You could do that as well. Yeah, and then you don't need any knowledge of structs. You could just say, hey, I get this number, gives me this address, and if I add 10 to it, it gets me that one, and I know where the target is. You could do it that way, and then you don't need any knowledge of structs.
But I've been trying to go through and use the structs, and it's still not working out.
Okay. If you do the trial and error thing and that method, go back and validate that, yeah, it is that size struct. Anyway.
You can use size up. I think you can.
Oh, inside the debugger? Yeah, you could use the size of thing in the debugger. I didn't give you so the reason I didn't give you that was, okay, well, yeah, you could use that. Yeah, sure. There's a lot of things you can use in the debugger, API calls. And I'm glad you found that, because that means you're comfortable enough in the debugger that you've started figuring out the more advanced features of it. Yeah, yeah, yeah. Yeah, in fact, if you're Googling GDB and figuring out all the things that GDB can help you with, then, yeah.
Yeah, every time I go to the 2 Center, I learn a new GDB call. I'm like, oh my gosh, that's...
Okay, that's a good thing. Yeah, yeah. So another tool in your toolbox, and once you have enough of those tools, if you revisit these binaries after you have all these GDB tools, you should find it so much easier. And that, yeah, because you've ramped up your knowledge. All right, so ARM, we just did x86, and so this isn't anything in your chapter or in your book. This is cobbled together things about ARM that help people understand why ARM is winning on mobile and why x86 is winning on the server end. And I actually talked about this a little bit at the beginning of class because someone had brought it up, but I'll talk about it more formally now. So the ARM history is called the Acorn RISC machine, and it's from Britain. The design was initiated in 1983 in response to a design philosophy out of UC Berkeley. And that'll be on the next slide. Their first implementation of this kind of machine was 1985. What's interesting about ARM is its licensing model. There are many people who can fabricate ARM chips, whereas typically Intel is the only one producing the x86 and AMD. But the whole model of this architecture is to have other people run with the architecture and implement their own things. Okay, so they don't produce their own chips. Companies customize this base CPU for their products. The most famous example is PA Semiconductor, which was a startup company that was basically designing ARM fablessly. So they didn't have a fab, like Intel has the design and the fabrication. These folks were just doing the design and then outsourcing the fabrication elsewhere, so fabless semiconductor startup company. And they were interested in using the ARM architecture to build a system on a chip. So your networking hardware is on the chip, your graphics is on the same chip. So they wanted to build it all in one and then embed that in something like a phone, a mobile device. And at that point, Intel's chipset was not built for that, right? Intel's motherboard was a CPU, and then on the motherboard you have your network card, you have your, the PCI slot, you got your graphics. So it wasn't set up for that. And so this is the reason why you started having, ARM designs being, built into single devices.
So if they're all still on the chip, they all like caches then? You don't have to drop it very far?
The caches are all on chip. Well, the caches are on chip on an Intel processor as well.
Like the graphics and the network, is that just right there?
It's all there. It's all on chip. Yep. Yep. And now some of the Intel packages have that as well. You see some of the more modern processors have the graphics on there. In fact, I think I saw it. Yeah, they all have it built in. The networking stuff, not so much, but Intel does have finally got around to adapting its design to try and get systems on chips. So they do have some stuff in this space within the last several years, but the train already left the station pretty much on this kind of stuff. Okay, so it's estimated that they make like a dime, and this is an old number. They probably make even less now, and it's just on royalties and licensing. 98% of all mobile phones in 2005, and I would imagine that number is higher now. Anyone have a Windows phone here? What's it? You do? What?
It was free with the contract.
It's free with the contract? What's the processor on it? Do you know? I don't know if that's hard. Don't think it is. But yeah, not many. So it's known to have better per watt performance, and this is important, per watt performance, versus the x86. And it has a lot less legacy instructions to implement because they more or less started from scratch, whereas the x86 design started as an 8-bit design in like the late 60s and early 70s, and then it went to a 16-bit, then 32-bit, now 64-bit. So it had all these iterations and all these instructions to support, and so yeah.
So are ARM chips, can you swap and replace and upgrade them like you can with?
Not at all. So one of the things about having Intel designing all of the x86 chips that they can do pin-compatible chips that can swap in and out. I don't know, have any of you done that? Swapped out your Intel? You have? Okay. I have. Is it hard? Just pop it off? Okay, so pin compatibility is something Intel can do.
Pop it off, put on some thermal paste.
Right, so ARM is different. Everyone's doing their own. I mean, the internal architecture is the same, so the programs don't have to change. But there's no standard. You would do your own custom thing because that's what you're allowed to do. Yeah, I'm imagining. Or has someone else fab their. Yeah, I believe so.
But they're all to a standard.
They're all executing the same instructions that are defined by ARM.
So on ARM and Android and ARM and iPad, they have the same performance? Because sometimes when there's a new iPhone, I mean, I thought because they're both ARMs.
Oh no, but who fabbed the
Okay,
it's a different
Okay.
different design. Like even though the architecture, the instruction set architecture is the same, you can tweak it. You could put 6 cores on there, or just make it 1 core, or you can clock it, faster or slower. These sorts of things. Yeah. Overclocking, yes. ARM was brought about from this Berkeley project in the early 80s, and this was this reduced instruction set machine architecture. And so this was a reaction against x86, basically these complex instruction set machines, and actually Spark as well, which is Sun's processor. So the idea was to implement fewer instructions and to take these complex instructions and implement them using multiple simpler ones. So we've seen the opposite with x86, right? You see multiple simple ones being executed over and over again, and Intel's like, I'm going to create a new instruction that does both of those things in one step, but because I still have programs that are using these separate things, I have to keep those in the architecture as well. So yeah, you can really speed up that operation, but it's more silicon that you've just had to put on your chip. And this is where the power goes, right? So now I have smaller instructions and this complex instruction both implemented, and that there's a power cost and there's an area cost, and this is where the trade-off is. Great for performance, so if you're on the server backend and you've got it plugged into the wall, and you've got water coolers and water cooling, yeah, and then you're like, yeah, that's what you want. If you're Google and you need to crunch away at something and give a route back like within 1 second, there you go. You need that power, and that's where you would use an x86 processor for that. Okay, so smaller execution unit. It's more efficient in terms of power as a result. Another interesting thing about the architecture is that there are only loads and stores to and from memory. That is a separate thing versus x86, where one of the operands, like for an arithmetic operand, could actually be a memory location. And it's both a load and an arithmetic computation and potentially a store in one instruction. So in an ARM, you load it from memory, you do the add, you store it in memory as 3 separate instructions. And that's just sort of like a microcosm of everything in ARM.
That's kind of interesting that they didn't even they didn't even split up that. Even though that's like one of the biggest things that everybody always has to do. You always have to do something with memory at one point. And they didn't even speed up that.
Yeah. Well, yeah. So, another interesting thing is uniform size instruction. So in x86, because the instruction set is so huge, they have 8-bit instructions. They have 8-bit opcodes. They have 16-bit opcodes, and you have to, in the instruction decode, it's like a parser. You have to decode the instruction is not simple. Whereas with ARM, there's basically 2 kinds of modes, and they're both fixed size, uniform size instructions. So it's like a table lookup. That's all you need to do to look up an instruction. Okay, in terms of the ALU, some of the features that ARM has, they built conditional execution into a lot of their instructions. You saw earlier we had this conditional move, where you put your conditional inside the execution unit, and you never have to block the control flow of your program and then stall on that branch. You just throw that into the data execution unit and let the results speak for themselves, and then you're allowed to prefetch more instructions without blocking. And so, yeah, less power loss due to stalled pipelines on that conditional branch. And then no need for branch prediction logic. So x86 at one point had all sorts of logic trying to get the branch prediction correct, and then logic to unroll computation if they didn't guess correctly. That kind of stuff costs you a lot of power. Another thing is that a lot of their ALU instructions allow you to do bit shifting on the operands before doing the operation. So this built-in barrel shifter in the ALU, so it's sort of like, when you do the multiply and the add on the same instruction in the addressing unit in x86, so the LEA quad, you could actually do a multiply and then an add in one step. The idea is similar here, but it's rather than it being in the addressing logic, it's built in natively into the ALU instructions. So everything could be barrel shifted, like shift left or shift right, before you call like the add or the multiplier, these sorts of things. Okay, so bit shifting and ALU operations in one. And then they also support 3 operand instructions where you have a destination and 2 source operands rather than just 2 operands in which one of them is a destination, like in x86. Yeah.
Does that take any more computation time? Like, does that take another set of, like, does that read as 2 cycles or still as 1?
Which one? This?
R equals
no, it's just different destinations. Different underlying plumbing, I would say.
I
But,
just want to make sure, because you were talking specifically about like storing variables, like doing memory, or doing operations and then having to store to memory. And then this would be a way that you could do operations and then store to memory, possibly, right?
Oh no, no. So this would be a register, and then after this, you would store this result. So you have the load, 3 loads, or maybe this is a register already, 2 loads at least, assuming that they're not in registers already, and then 1 store, yeah, if you want to store it out. But you would try and keep things all in registers. We'll actually see this in the next chapter, to try and keep things in registers. Control state features that are interesting. It's got these shadow registers. We talked about shadow registers before when we talked about hyperthreading. It's very similar to Intel's hyperthreading. And so if you have your process is running and all of a sudden you get an interrupt and you need to switch over to like exceptional processing, typically you have to save all the registers, the register state of the process that you're interrupting. So that typically would go onto the stack in memory. And of course, that's not what you want because memory is typically slow. So they built in these shadow registers so that you can basically flip the register set. 2 sets of registers, and you flip which one you're using based on the interrupt. So it's akin to Intel hyperthreading. Another interesting thing is this link register. So when you do a call on x86, you're pushing the return address into memory. So this is an optimization to avoid that when you're in a leaf function. So in a leaf function, you're always going to return back to the caller. And so what they do is they have this link register, and they store the return address in the link register rather than onto the stack. And then when you hit that return, you just read what is in the link register and then return from there. Yes.
Sorry, doesn't that make it more secure? Because that means that the return address is actually somewhere in the registers, not in something that can be overwritten with a function call, right?
So you can't overwrite the leaf function's return address, but the other stuff in the stack is still stored, right? The non-leaf return addresses are still on the stack. I mean, because if the leaf function, if that function that was in the link register called another function, then it would have to store the old link. It would have to store the link register beforehand. Yeah. So security-wise,
not really.
Yeah, not really. What is actually so this actually is from last year. Intel decided to put all the return addresses in a separate stack. So that definitely avoids the buffer overflow. I forget what technology they called it, but that's in the. It hasn't hit the CPUs yet, but I believe next year the x86 CPU will now have a separate stack for return addresses.
So you have 2 stacks technically in one CPU?
Yeah, a
So
different
one
area
stack
for the
running
return
in the
addresses. Yeah, and then I don't know what I'm going to do with my binaries at that point. Won't be able to do the stack smashing.
Well, I mean, they're going to be like i8, so no one's going to be able to afford them for another 5-6 years.
Yeah,
you know?
yeah.
Like,
Or maybe there's a way to tell the compiler not to use that extra stack. Actually, that might be. I don't know if it's going to be transparent or not. But if it is transparent, then I have to find a way to turn it off. I'm sure there will be a way to turn it off.
Probably to like a lot of code when you kind of like will be different now. You're required to write like in a different way your code when you talk to the registers.
The compiler.
Also, the compiler will be a mediator. He'll be like, okay, I know what does that.
They'll change the compiler based on the architecture, and all compilers figure out what architecture am I compiling to, and then they'll produce something. But one of the things, so if you get a Linux distribution, they have to compile to the least common denominator. So if you run Ubuntu, it's like, well, I got to make sure that I'm running to something that will run on everything, like the official distribution. And this is why people who really care about performance will end up compiling their own using the processor that the compiler knows it has. But if that loses some portability, that means you can only run on certain platforms.
I feel like people running really advanced and obscure modifications of Linux, you just download the binaries.
You have to make sure your architecture matches. If you don't want to build it yourself, and you want every bit of the performance, then you would have to download. Yeah, so they phased out 386 finally in Ubuntu. So yeah, now you can't get that. Yeah, you can't get that from there. Yeah. All right. So ARM is trying to go from the one end, from its end towards Intel's end, and Intel is trying to go from its end to the ARM end. And so you see this in their chips that they're releasing. You see Intel really focusing on low power, these sorts of things like that Surface tablet with the chips that are going in there. So they're really trying to get into mobile. So in order to compete, ARM is going after x86 at the high end. And so you see stuff like single instruction, multiple data instructions. This is typically for high-end scientific or multimedia workloads. You see versions of ARM supporting SIMD instructions for multimedia decoding, which is the MP3 or an MP4, AES, which is encryption, and SHA, which is also encryption support. Hardware virtualization for virtual machines. They want to support that. Direct bytecode execution. So this is compiling, getting Java bytecode to run natively. And then doing stuff like adding security extensions, like the no execute page protection that we saw for stack smashing is very helpful. Okay, so to summarize, key architectural differences from x86 versus ARM, CISC versus RISC, legacy instructions being supported at the expense of per watt performance. And so an example of Intel going towards the ARM market is this Atom processor, which they stripped it down, the 8386 core. They tried to strip all the cruft away and then ship that as a more power-friendly Intel CPU. And this was once a candidate for the iPad, but then it got scrapped. I guess they didn't do quite a good enough job. State pushed onto the stack versus swapped into via shadow registers. Separate bit shifts versus built-in bit shifts on the ARM side. Memory locations usable as operands versus explicit load and stores from memory. Mostly 2 operand instructions versus 3 operand instructions. And so I have a version of the CTF that you guys are doing for ARM, compiled for ARM. So if you like ARM assembly and you want to learn it, I can ship you some binaries, and now would be the time to do it if you've gone through the x86 stuff and you actually want to see how to subvert the thing. We played all of these levels again in our CTF group on ARM, and they're equivalent.
So you have to get like a Raspberry Pi to run that?
Yep, we had a Raspberry Pi. Put the binaries on there. Yeah.
Have probably a version of distribution of Linux.
Yep. Linux runs on there.
It is a Raspberry, something like that.
Yeah.
It's a Debian subset.
Mm-hmm. So yeah, you could do it on a Pi. I can give you a zip file of all those binaries if you want to. Send me an email. So remember, I'll send you those binaries if you want to try your ARM disassembly out. Obviously, the instruction text hasn't been changed to indicate that you're supposed to link parameters and stuff like that. You have to do the ARM calling convention, not the x86. So you'd have to figure that out. That kind of stuff. The other differences, and these are sort of, one of the biggest ones is that Intel is the only producer of the x86 chips and designs. And because of this, they're a bottleneck. Like, technology moves really fast, and you want to be able to take a technology, alter it to suit your needs, and then upsell people on it, right? You can't do that with Intel. Intel is the one and only company with x86 chips and designs, you're getting what everyone else gets. And if you want a feature added that you think is essential for your business, yeah, try getting Intel to implement it and shipping you a chip. It doesn't happen. So, there are technical reasons why ARM won, but the non-technical one being that sort of the licensing model is as important because, this is what allowed Apple to differentiate itself with its processors. And so that was a key thing. Intel had an ARM. It had bought this, I think it was called X-Scale at the time. It was producing ARM chips, and then it abandoned it because it wanted to do this Atom thing. And it turns out maybe they shouldn't have abandoned it. But they abandoned it, and so the mobile devices are mostly ARM now. Okay.
What about AMD? Is similar to x86?
Mm-hmm. Yeah, so they're mostly x86 on the server end as well. Yeah. I don't think they have a mobile. I don't think they even tried to enter the mobile space with x86.
Their market is a very different kind of market too. They're going mostly for consumer low cost electronics.
I was just wondering if they have the same architecture as the x86.
As x86, yeah. Oh. So AMD was licensed the 486 design, and then they were the ones who came up with the 64-bit x86, and then Intel adopted that. So yeah, they're all x86. Okay. At the time, the speculation of why Intel abandoned ARM was that they believed that their process advantage, so Intel has always been the first to the new process, would eventually outweigh the power loss, like the fact that they're power hungry. Like if they could always be a couple generations ahead in the fabrication process, they could eventually catch up on power. Because the smaller your transistors, the less power you consume. So there was that one thing. The other thing was they believed that leakage current, which is basically the area, and this goes hand in hand, the area of your chip, if you shrink it enough, then the leakage current is going to be the dominant factor versus the switching current for actually turning transistors on and off. So that was another thing. So it is believed that was the sort of the strategy at the time as a motivation.
Weren't they not first to market though with x86? Because I thought AMD was first to market for x86.
64-bit, yes.
64.
Yeah, and then they adopted it. So some people speculated that they did have a 64-bit x86 design that they were working on, and as soon as people, so Intel was pushing this Itanium architecture and it's trying to get people completely off of x86. It's like, yeah, there's so much ugly stuff in x86. We want to completely abandon it, and when we go from 32-bit to 64-bit, we want people to completely switch architectures. And so, but on the side, that they were like hedging. And then they had a x64 architecture there, and then when AMD really started to sell a lot of 64-bit servers, then they had a chip in place. Yeah.
Huh, that's interesting. It's a good marketing strategy.
But I think in 2006, the mobile devices didn't look the same way, and neither so I think they underestimated the market because there is on those D8 where it was Steve Jobs and Bill Gates, and when Bill Gates was talking about mobile devices, Steve Jobs was talking about the iPhone, but he was like, no, there will be a surface and will be a table, and we'll cleaning things on the table. So I think they had a different perspective of how the Internet of Things, they were believing, I think, in a different type of future.
Yeah, could be. Yep.
They were like, why you need that?
Yeah.
I'll take your computer anthropology class. Just let me know.
I need to find something. Well, the thing is, I'm subscribed to this Internet history list, and there's a lot of anthropology in there that's going to go by the wayside. So guys like Vint Cerf, who's the father of the Internet, he talks about certain things and design choices for the Internet protocols. And then you're like, wow, all of this stuff is fascinating. It's not really that technical. Semi-technical, but the mailing list, I think you could search for it. Yeah. Internet history is the mailing list that I sort of frequent. But
you gotta know that there's somebody backing up all that information somewhere.
Yeah. Hopefully someone writes a book.